Good morning, everyone. My name is Aryan, and today I will be presenting my material science assignment on one of the most fascinating materials in modern engineering, carbon fiber. Carbon fiber has completely transformed industries due to its unique set of properties. It's five times stronger than steel, twice as stiff, yet significantly lighter than aluminium. It's no surprise that it has become an essential material in aerospace, automobile engineering, sports, and even biomedical devices. But what makes it truly extraordinary is how everything from its atomic structure to its manufacturing process contribute to the incredible performance. Let's begin by looking at atomic structure and electronic configuration. Carbon atoms in carbon fiber are arranged in hexagonal lattice structure, quite similar to graphite. Each carbon atom is sp2 hybridized, which means it forms three strong sigma bonds with the neighboring carbon atoms. The remaining electron forms a pi bond, and these pi electrons are delocalized across the structure. This delocalization leads to good electrical conductivity along the plane and also contributes to the strong covalent bonding that gives carbon fiber its strength. The electronic configuration of carbon is 1s square, 2s square, 2p square, and through hybridization, the 2s and 2p orbitals form the 3sp square hybrid orbitals required for this bonding pattern. Moving on the crystal structure, moving on the crystal structure, carbon fiber resembles stacked layer of graphene sheets. These layers are strongly bonded in the plane but are loosely held together by weak van der Waals forces between layers. This is why carbon is extremely strong along the direction of fibers but more brittle or weak when forces act perpendicular to fiber direction. This property is particularly important in composite design where the fiber orientation is chosen based on the direction of expected stress. Now let's talk about synthesis procedure. Carbon fiber is typically produced from a precursor called PAN or polycrylonitrile. polycrylonitrile. The process consists of several steps. First, there is stabilization, where the PAN fiber is heated in air at around 200 to 300 degrees Celsius. This helps make the polymer thermally stable by initiating oxidation. Next is carbonization, which happens in inert atmosphere like nitrogen at temperature between 1000 to 1500 degrees Celsius. This step removes non-carbon atoms like hydrogen, nitrogen, and oxygen. The result is carbon-rich structure. Finally, there is graphitization, which occurs at even higher temperature, above 2500 degrees Celsius, to align the carbon atoms into a more ordered structure. This step is not always required, but when done, it improves electrical conductivity and stiffness. To better understanding where carbon fiber fits among other forms of carbon, we can look into the phase diagram as you can see here. The phase diagram shows that at high temperature and low pressures, the graphite phase is stable, which is the phase carbon fiber aim for during graphitization. This helps enhance their strength and conductivity. Coming to the properties, as you can see in properties table, carbon fiber is packed with advantages. Electrically, it behaves like a semiconductor or conductor depending on how it's processed. It's non-magnetic, which is useful for sensitive electronic and MRI compatible devices. Electromagnetically, it has excellent shielding properties, make it deal for aerospace and satellite applications where interference needs to be minimized. Optically, while carbon fiber is opaque, It can absorb infrared and visible light, which is even used in some stealth applications. So, to analyze the morphology of carbon fiber, several techniques are required. The techniques are SEM, or scanning microscopy, shows us surface textures, defects, and fiber orientation. TEM, TEM, or transmission electron microscopy, gives a deeper look into the crystal structure and internal layering. Then we have AEM, or analytical electron microscopy, gives a deeper look into a crystal structure and making internal layering. Then we have AEM, which combines imaging and chemical analysis to study the composition and structure of nanoscale. These methods are crucial in quality control and research, helping improve performance and reducing manufacturing defects. Speaking of the nanomaterials involved, as nanomaterial aspect, carbon fiber is essentially a nano-engineered material. It contains layers of graphene at the nanometer scale, which contributes to its mechanical strength and electrical properties. It also shares similarities with other nanocarbons like carbons, nanotubes, and graphene, especially in terms of surface area, electrical properties, and bonding patterns. These nanoscale structures is what allows it to perform far better than traditional bulk materials. Now let's look at the manufacturing. As you can see in the chart, first the precursor is spun into fibers. Then comes thermal stabilization in air, followed by carbonization in an inert atmosphere. After that, surface treatment is done to improve bonding. When these fibers are combined with resins to form composites, finally, a sizing agent is applied to protect the fibers during handling and weaving. This entire process is carefully monitored to produce high performance carbon fiber with consistent quality. Finally, I would like to talk about some of the learnings and material science from the material science course. Through this assignment, this project helped me appreciate how deeply connected structure and properties are. Just a change at the atomic level, like hybridization or bond arrangement, can drastically change a material's behavior. I also understood how various synthesis methods, processing techniques, and characterization tools come together to engineer a material like carbon fiber. The course gave me a new perspective on how materials are selected, studied, and optimized, not just for theoretical knowledge, but also for the real world application. To conclude, carbon fiber is more than just a strong and lightweight material. It's a perfect example of how science at the atomic level translates to cutting edge technology. Whether it's aerospace, sports, or medicine, carbon fiber is a prime example of what modern material science can achieve. Thank you for listening, and I hope you found this presentation informative. धन्यवाद.